So the next homework that you work on is going to have integrals that require inverse trig functions in order for you to resolve them. And in particular, what we're going to be interested in is trying to find antiderivatives of functions that either have the sum of two squares in the denominator or a difference of two squares in the denominator. And in the previous homework, what we saw was that the derivatives of the inverse trigonometric functions all wound up with sums or differences of two squares in the denominator. So we're going to use these derivatives from the previous homework assignment as a building block to work backwards. When we're doing this, we want to recognize that if we have the sum or difference of squares in the denominator, that we can think of things in terms of right triangles, and this is how we derived these things in the previous video. If we have a difference of two squares, then this is a 1 squared is 1. So the first thing that's being squared, if we have a difference of squares, is a label for the hypotenuse. And then the second term that's being squared is one of the legs of a right triangle. And then the square root of the difference of the squares gives you the other leg. Or if we have the sum of squares, that's going to be associated with a right triangle, where we have the two expressions being squared as the legs of the triangle, and then the square root of the sum of those squares as the hypotenuse. So when we have sums or differences of squares, we want to recognize that we're really seeing, in some sense, the Pythagorean theorem showing up. The other important thing to recognize with these derivatives of inverse trigonometric functions from the previous homework is that they differ only by a negative. So the arc sine, the derivative of the arc sine and the arc cosine differ only by a negative in the numerator. So we don't need to use both functions if we're trying to integrate things that have the square root of a difference of squares. We can just say, hey, we're only going to use the arc sine as our tool. If we look at the arc tangent and the arc cotangent and their derivatives, we see that their derivatives differ only by a negative sign. So it's customary only to work with the arc tangent. And finally, the arc cosecant and arc secant, if we take their derivatives, the derivatives differ only by a negative sign in the numerator. So it's customary to allow ourselves to just work with the arc secant function. So if we throw away the three that only differ by that negative sign, we're left with the arc sine, arc secant, arc tangent. And you could think about, well, what if I wanted the antiderivative of 1 over the square root of 1 minus x squared? Well, if we know the derivative of the arc sine is 1 over the square root of 1 minus x squared, we could just integrate both sides of this derivative with respect to x. We could integrate with respect to x. The antiderivative would cancel the derivative, and we would get, hey, the arc sine of x is the antiderivative of 1 over the square root of 1 minus x squared. We could integrate both sides of the derivative of the arc secant. Whatever we do to one side, we do to the other. The antiderivative would cancel. The derivative would get, hey, the arc secant of x is the antiderivative of 1 over the absolute value of x times the square root of x squared minus 1. And we could do the same thing with the derivative of the arc tangent. We could integrate both sides. Integration would cancel differentiation. We'd be left with the arc tangent of x equaling the antiderivative of 1 over x squared. And then we would recognize that, hey, we always, when we integrate, add on that constant of integration. So this would be nice if we always had a 1 in this position, but we're going to want to be able to deal with things that have not just a 1, but any constant a. What happens if we have a squared minus u squared, where a is just some constant? So in the previous slide, there was always a 1 in this position, but what happens if there's an a instead of a 1? Well, we get almost exactly what we would get by integrating things in the previous slide, but we wind up with this tweak factor in 2 of the cases. That deals with the fact that there's a chain rule going on. So to justify this, we could justify it in the context of this, and then recognize that how you would justify the other 2 is similar. So what we could do is say, hey, instead of the arc tangent of x, so here I had the arc tangent of x, what happens if I have the arc tangent of u over a? So let's just start with the function that has y equals the arc tangent of u over a. And then we could do, similar to what we did in video 1 of the previous homework, we could say, hey, if I wanted to know the derivative of the arc tangent, I could start by taking the tangent of both sides. So I get tangent of y equaling the tangent of the arc tangent. That would cancel and leave me with u over a. And then I could differentiate both sides. So if I did that, I would get the secant squared as the derivative of the tangent, but I would need to multiply by y prime by the chain rule, and the derivative of u over a would just be 1 over a. And then I could multiply both sides by the cosine squared of y, because that's the reciprocal of the secant function. So y prime would equal 1 over a times the cosine squared of y. And then we recognize that from this step that this is just describing a right triangle. And I could draw that right triangle in. So it's just similar to what we did for the derivations in the previous video. Hey, you input an angle into the tangent function and you get opposite over adjacent. So the cosine squared, we could get the hypotenuse here, tilt my head. This would be the square root of the sum of the squares of the legs. And so the cosine squared, we'd get y prime is just equal to 1 over a. And then we would need to square the cosine, but the cosine is going to be adjacent over hypotenuse. And so we get square root a squared plus u squared. And the squaring is going to give us an a squared in the numerator over a square root of an a squared plus u squared down here. And then you're going to wind up with y prime equals, that a is going to go into the a squared. We're going to be left with an a over the square root of a squared plus u squared. And what is y prime? Well, it's just the derivative of the tangent function with respect to variable u. So I'm going to erase this to give myself some room. This is just du of the arc tan of u over a. That's what y prime is. And so if we integrated both sides with respect to u, so we do this on both sides, you get the antiderivative of the derivative is just the arc tangent of u over a. You get the arc tangent of u over a. This a is a constant, so it would factor out front and leave behind a 1. And then you could multiply both sides. You'd have the arc by 1 over a, so you'd get 1 over a arc tan of u over a is the antiderivative of 1 over the square root of a squared plus u squared du. So a squared plus u squared, which is what we've got going on up here. So you could justify, you could start with what we did with having a 1 here in each of these positions. And then you could say, well, what if instead of x inside of here it was a u over a? How would that change how things looks? And you wind up in these two cases getting that little tweak factor. So these are the formulas that we'll use in subsequent videos. And then I will hopefully remember to put this box on the cover page of your homework assignment so that you have it for a quick reference.